Hello, good morning and good afternoon, good evening to everyone that's joining us from all around the world. I hope everyone is safe and healthy and slowly starting to get back to a normal life, at least in some areas. My name is Jennifer McConnell and I'm a product manager here at Protochips. And we're really excited to bring you this joint webinar between Gamry Instruments and Protochips today. Gamry Instruments' expertise lies in electrochemistry for various applications, and Protochips' expertise lies in MEMS-based in situ transmission electron microscopy, or TEM. And the two companies have actually combined forces for years to offer a really unique nanoscale solution for battery corrosion and fuel cell catalyst research via in situ electrochemistry liquid cell TEM. So today we're going to have presentations by Dr. David Loveday from Gamry Instruments on the basics of electrochemistry, followed by Dr. Madeline Dukes from Protochips on integrating that electrochemistry into TEM for in situ and operando types of experiments. Then at the end, we're going to have a short question and answer session as well. To give you a little bit of background on our presenters today, Dr. David Loveday is a sales and technical expert that's been with Gamry Instruments for 19 years. He earned his PhD in electrochemistry from University of Bristol in the UK. And prior to joining Gamry, he was a research associate at the University of Texas at Dallas. Dr. Madeline Dukes is a senior application scientist at Protochips and earned her PhD in chemistry from Vanderbilt University in the US. And since then, she's built up more than 10 years of experience in the field of liquid cell TEM. And she's traveled the world multiple times over, working with our customers to improve liquid cell TEM technology and develop new sample preparation techniques for a broad range of applications. So a couple of housekeeping items before we begin. If you have questions during the presentations, please enter them into the question chat box on your screen, and that's where we'll pull from when we go into the question and answer session at the end. And another thing, just real quick, Dr. Dukes is here live with us today and we'll be answering questions at the end. However, her presentation you'll be watching is recorded. The internet where she lives is a little spotty and she didn't want that to interfere with your experience today. But we will get a chance to talk to her live later as well. Without further ado, I think it's probably time we should get started, and I'll hand it off to Dr. Loveday to go ahead and do so.
Good morning, everyone, and thanks, Jen, for introducing me, and thanks to everybody for attending today, wherever you are. I'm glad you were able to take the time to do that. I'll be giving a short presentation today about an introduction to electrochemistry, potentiostats, and a little bit about maybe how they work, and also about the types of experiments that you can use with the potentiostat. So without further ado, let's get going. Jen, I don't have control.
Sorry, you do. Go ahead and hit the arrow button on your keyboard.
Okay.
Perfect.
So what is electrochemistry? Electrochemistry is the branch of chemistry that involves the exchange or movement of electrons accompanying a chemical change. It's a study of electron transfer reactions. In a generic form, you can draw in a reaction like the one on the screen. So for an oxidized species gains electrons to become reduced. Oxidation is the loss of electrons. An example of that is a dissolution of iron, which is a kind of a corrosion reaction. And reduction is the gain of electrons. And an example of that is hydrogen ions becoming hydrogen gas. Here we have a representation of electrochemical interface. We have a metal surface, again iron, in contact with the electrolyte solution, which might be, for example, water with a salt like sodium chloride dissolved in it. An alternative representation here shows the interface more closely. in electrochemistry, everything of interest takes place at the interface between the electrode and the solution that it's in contact with. On the left, we have the metal electrode surface with some potential, and it attracts ions from solution of the opposite charge, which leads to an excess of charge at the surface compared to the bulk solution. Ions may also be absorbed to the electrode. So the processes at the surface that cause current to flow are firstly so-called Faradaic processes, where current flows is due to the result of electron transfer redox reactions. Redox is an abbreviation of reduction oxidation. Current can also flow, though, due to the capacitive nature of the electrode. When the potential of the surface is changed, a current, as ions are attracted to the surface, current will flow. And it's difficult to separate these two processes. Just want to introduce some electrochemical quantities to get everybody on the same page. First, when we talk about potential, that's the voltage that's going to be used as the energy of to measure the energy of the reaction. It's equivalent to wavelength in optical spectroscopy, and potential is the driving force of the redox reaction. Its units are volts. The second important quantity is the current, designated I, and electron flow. The current is the electron flow as a result of a redox reaction. Current measures the rate of the reaction. It's in electrons per second, and oxidation and reduction currents have different polarities. The unit of current is amps. So what is a potentiostat? I just want to, so electrochemical reactions are controlled through the use of a potentiostat. So the potentiostat is an electronic instrument that measures and controls the voltage difference between a working electrode and the reference electrode, and it measures the current flow between the working electrode and a counter electrode. Sometimes we want to control the reaction to control reactions by controlling the current that flows in the cell, and for this we need to use a galvanostat. So a galvanostat controls the current between the working and counter electrodes, and potential can also be measured. Most potentiostats that you can buy can also function as a galvanostat. For those of you unfamiliar with potentiostats, here's an example of a Gamry to potentiostat called the reference 600 plus. So here's another example of a schematic of how an electrode in solution with a potentiostat works. What the potentiostat does is it sets the electrode potential so that electron transfer goes downhill. So in the case of a reduction, we're going to raise the potential of the energy of the electrons so that they can transfer from the electrode into the molecular orbitals of the ion in solution that we're trying to reduce. Conversely, when we're going to do oxidation, we're going to lower the energy of the electrode so the electrons can be transferred from the molecular orbitals in solution into the electrode. So a potentiostat generally requires 3 electrodes, or there are cases when 2 electrodes can be used. We have the working electrode, which is the electrode where the reactions of interest are going to take place. The reference electrode has a constant, and is an electrode with a constant electrochemical potential, as long as no current flows through it. And then the counter electrode completes the circuit and is generally inert. The current that flows into the solution via the working electrode leaves via the counter electrode. Why does a potentiostat have 3 electrodes? We'd like to study the electrochemical events taking place at one specific electrode, the working electrode. The use of a 3-electrode potentiostat with a separate reference and counter electrode allows the potential at the working electrode and the current at the working electrode to be measured with little or no interference or contribution from the other electrodes. Essentially, we're isolating the current voltage behavior of the working electrode by measuring the voltage of that electrode with reference to a reference electrode that doesn't have any current flowing through it. Here's a representation of a standard electrochemical cell that you might use in the lab. In the cell that you'll use in the case of a TEM obviously is on a much smaller scale, but the principles are the same. So we have a setup where we have a working electrode, a reference electrode, in this case inside a glass tube filled with solution to make it in contact with the main cell, and a counter electrode that may be in an isolated glass tube that's on the right there. We may also want to have a way to pass gas into the solution to prevent oxygen interfering with our reactions. And in addition, we also might have an additional port that might be used for a temperature probe. The cell, in this case, the cell is made of glass, but it also has a glass water jacket to control the temperature of the cell. So the working electrode is an inert, generally can be something like an inert platinum disc electrode, which is polished. In this case, it's 3 millimeters in diameter. The overall length of the electrode in this case is about 12 centimeters, and that would be, and it's encased in an inert KEL-F tube. Counter electrode is in general is an inert material. In this case, could be a platinum wire, and as I pointed out when I showed the cell, it is sometimes isolated from the main cell using a fritted glass tube to stop any products that are made at the counter electrode from interfering in the main cell. Reference electrode is a general reference electrode is a glass tube that contains the parts for the half cell reaction that's going to have the half cell that we're going to reference all our potentials against. At the right hand tip underneath the black covering is a porous glass membrane that allows the reference electrode ions to pass through the reference electrode into the solution, allowing it to be in contact with the solution but to avoid too much contamination. We need to pay special attention to the reference electrode in general, because for a potentiostat to work correctly, the reference electrode needs a low impedance or resistance. And this can be achieved by having the glass membranes that are very porous, and in general we want to have avoid long capillaries that connect the reference electrode to the main cell. Potentiostats in general are less forgiving of high impedance reference electrodes than devices like pH meters, because the control of the voltage in the cell is made through a feedback of the potential that's read at the reference electrode. And if this high impedance reference electrodes can slow down this control. So when you get see a problem in your cell, it can often be attributed to the reference electrode. So specific requirements for TEM measurements. Because of the in the TEM cell, the electrodes are on a much smaller scale than the general lab cell that I showed. The ability to measure low currents is very important, and a specific example is the reference 600 potentiostat that I showed, has a full-scale current range of 60 picoamps. And what that means is that it allows us to measure, potentially to measure femtoamp currents. Another important feature is that the potentiostat is isolated from earth ground. The reason for this is that the TM in general is grounded for safety reasons and for the way that it works. And a grounded potentiostat may cause problems with the TM. At a minimum, it may be difficult to measure the current in the cell if you use a grounded potentiostat. So, and Gamry pays close attention to ground isolation in the design of its potentiostats. So what are the electrochemical experiments that we can perform? I've indicated three application areas that people have used the TEM cell to study. These are corrosion, physical electrochemistry, where they look at fuel cell catalysts, and battery materials. In the corrosion field, the experiments that people use are the polarization resistance, which is a kind of linear sweep voltammetry, and also Tafel plots. The polarization resistance experiment is usually over a small voltage range, whereas a Tafel plot gives you information over a wider voltage range. In physical electrochemistry, the main experiments are cyclic voltammetry, where the voltage is swept at a constant rate forward and backward between different voltage limits. Linear sweep voltammetry is a single sweep version of cyclic voltammetry. And then we may also look at potential steps, where we step the potential from one level to another, or the equivalent in galvanostat mode, where you might step the current from one level to another. For studying of battery materials, most of the tests are done in the current control mode, where we want to look at charge and discharge to mimic the levels of the material in a battery. So for corrosion experiments, here's two examples. On the top left, we have an example of a polarization resistance scan, where the voltage is scanned from -10 or 20 millivolts below the open circuit potential to 10 or 20 millivolts positive of the open circuit potential. And the open circuit potential is the resting potential of the material that you're studying in the solution of interest. And on the bottom right, we have a potentiodynamic scan, which is a wider version of a Tafel scan of a stainless steel in sulfuric acid. And the different voltage levels put the material in different states that can be studied to find out its composition. So the electrochemical experiments that are used often for fuel cell catalysts are constant potential amperometry, or also potential steps, where you might, which is called chronoamperometry, where you step the potential from one voltage level to another, and also the cyclic voltammetry, where we cycle the potential between different potential levels. So for amperometry, on the top left, we show the voltage profile, where we go from a resting potential level to a point where some electrochemical reactions take place. And then on the bottom left is the corresponding current that is generated when you step the potential. And when you step the potential back, you get in general, get the current back. And a cyclic voltammetry example is on the top right again. I'm showing the voltage profile, which looks like a V, where we have a constant scan rate going from one level to another and back again. And the bottom left is the current response for in this case, it's potassium ferricyanide in solution, where the current in one direction is in the positive direction, and then when we reverse the scan, it goes in the other direction. The peak occurs when we get the rate of reaction. The peak is an indication of the electrochemical potential of the species of interest. In this case, iron 2 to iron 3. So for battery materials, we'll, as I said, we'll do the charge-discharge experiments, where we have a constant current, either positive or negative, that'll change the state of the material, and it mimics the state of the battery, of the electrode in a battery setup. And what we can do, we can put in a certain amount of charge or take out a certain amount of charge to achieve a specific state of charge. And when we do those experiments, this is experiments for a full battery material, but it's similar for a battery material cell. We'll have a period where we have a constant current, where the voltage will be increasing. In the case, if you see on the green line here, that's a constant current, and the voltage is going up till it reaches a certain limit, and then we hold the constant voltage to reach a steady state in that material. And then on the discharge, which are in the case of the blue lines, you have a current in the opposite direction, and the voltage drops, and we can pull out or put in a certain amount of current to reach a certain state of charge. So that's my basic introduction to the types of experiments that can be done. I thank you for listening today, and now I'm going to pass you on to Madeline, who's going to talk about the TEM part and in situ electrochemistry for the TEM.
Thanks so much, Dave. So I'm Madeline Dukes, and as Jen said, my presentation is pre-recorded due to my internet here at home, which I'm sure many of you have had to be dealing with over the last few months. So you understand the issues there. So without any further ado, let's go ahead and get started. Transmission electron microscopy, or TEM, is a microscopy technique that uses a beam of electrons instead of light to form the image. Electron microscopy enables specimens to be imaged at much higher resolutions than light microscopy due to their smaller wavelength. Thus, we can use it to image nanoscale specimens even down to the atomic level. In order to maintain a coherent, high-quality beam of electrons, the microscope column must maintain a high vacuum environment. This traditionally limits the types of samples that can be imaged, as the sample must also be stable under high vacuum. Electrochemists often use conventional TEM techniques to study the structure of electrode materials pre- and post-experiment. However, conventional TEM imaging does not provide kinetic or dynamic information. Technological advances over the last decade have led to the development of in situ TEM techniques. In situ techniques enable researchers to interact with the specimen by applying stimuli to samples directly inside the electron microscope. This allows us to study dynamic, changing systems and use the electron microscope as a real-time nanoscale laboratory to fill in the missing steps of dynamic, evolving processes that we can't observe by any other means. An easy analogy to understand in situ TEM is an example from photography. Our eyes are not fast enough to discern the movement of a horse's hooves as it runs. Early pre-photography paintings and drawings depict horses at full gallop with all 4 feet simultaneously on the ground. Not until 1878 were the missing pieces of the mechanism captured. These results showed for the first time that at no point during its movement were all 4 feet off the ground. Likewise, in situ TEM allows us to fill in the missing gaps in evolving processes at resolutions we can't see using other methods. Because a high vacuum is required for the electron microscope to operate, samples typically have to be dry in order to maintain the column vacuum. Thus, samples that are liquid or in hydrated states have to be processed either by drying, embedding in resin, or flash freezing before they can be imaged using TEM techniques. So how do we safely image wet samples in the TEM? The solution is to isolate the liquid between a pair of microchips, which Protochips calls E-chips. Each of these E-chips contains ultra-thin electron transparent membrane that isolates the sample from the vacuum and forms an in situ liquid cell. This enables us to safely image samples in their native liquid environment, preserving not only their hydrated structure, but their dynamic behavior as well. In this example, in situ TEM was used to study the degradation mechanism of a core shell platinum-palladium nanocatalyst particle. These nanoparticles show very promising catalytic activity, but when integrated into fuel cells, retain only 12 to 36% of their activity. Conventional TEM imaging of these particles pre- and post-experiment shows structural degradation and loss of surface area, which may be attributable to the loss of activity. Using in situ liquid cell TEM, researchers were able to observe and follow the degradation of individual catalyst particles in real time. This allowed researchers to pinpoint how different types of defects in the particle's platinum shell made them susceptible to different corrosion mechanisms. They identified 3 categories, color-coded in this movie: regular cubes with no defects, circled in orange, cubes with defects along the terrace, circled in blue, and cubes with defects at the corners, highlighted in green. The nanocubes that had a pristine platinum shell structure with no defects underwent a slow galvanic corrosion process, and the platinum shell remained structurally intact after etching away of the palladium core, and consequently, they retained their catalytic activity. However, if the platinum shell had defects in either the corners or along the terrace, that exposed the internal palladium to the electrolyte, and a much faster halogen etching process occurred. That resulted in collapse of the shell structure due to the pre-existing defects and a significant loss of catalytic activity. In this study, in situ liquid cell TEM provided a much more complete understanding of the factors that contributed to the overall degradation of catalytic activity when the nanoparticles were incorporated into a fuel cell. For electrochemistry applications, in situ provides an unprecedented opportunity to supplement traditional ensemble measurements with time-resolved imaging of evolving processes under operating or operando conditions. Integrating electrochemistry into in situ liquid TEM experiments, we can explore a variety of different applications, such as the formation of the solid electrolyte interface and dendrite growth in batteries, the aging and degradation of nanoparticles for catalysis, and the environmental effects on corrosion processes. In order to transmit the electron beam through the sample, TEM specimens must be thin, ideally on the order of several hundred nanometers or less. This is true for in situ liquid imaging as well. Thus, it's necessary to scale down from traditional bulk volumes on the order of tens of milliliters to sub-nanoliter in order to work within the transmissive and spatial confines of the electron microscope. Specimens are inserted into the electron microscope using a dedicated in situ TEM holder. The liquid from the sample and the electrolyte must be hermetically sealed between the microchips, called E-chips, which support the electron transparent membrane. The Protochips Poseidon Select system safely enables you to insert liquids and hydrated samples into the TEM to perform a wide variety of in situ experiments. A single sealing gasket sits between the E-chips and the TEM holder. A pair of E-chips enclose the sample, and the seal is formed when the lid is attached and the gasket is compressed. Integrated microfluidics and electrical contacts enables the delivery of liquids to the imaging region throughout the experiment, as well as stimuli for electrochemistry and temperature-controlled experiments. The Poseidon Select system is optimized for electrochemical performance inside the TEM. The unique miniaturized environment required for successful experiments means that Poseidon is optimized for low noise and ultra-low electrical measurements. The design of our E-chips isolates the electrochemically active area where your reaction is happening to the viewing window so that you don't miss any part of your experiment. This platinum sulfuric acid cyclic voltammetry plot demonstrates that the electrochemical measurements are not appreciably affected by the TEM's electron beam. The red line indicates that the beam is on, and the black line is the same experiment with the beam off. Accurate, reliable delivery of fresh electrolyte to the active area is critical when working with such small volumes to avoid electrolysis of the electrolyte over the course of the experiment. Fluid exchange between water and dilute sulfuric acid within the cell was tracked using electrochemical impedance spectroscopy, or EIS. Water was flowed into the cell, exchanged with sulfuric acid, and flushed again with water. This process was repeated 5 times, and the change in the impedance was measured using EIS to demonstrate the exchange of liquid. A typical electrochemistry experiment, a ferricyanide-ferrocyanide redox couple, shows the sensitivity of the system. Cyclic voltammetry, or CV experiments, provide insight into mass transport and diffusion-controlled processes. These measurements, performed with the Protochips Poseidon Select, exhibited characteristic oxidation and reduction peaks when using fast scan rates due to mass transport being dominated by diffusion, while at slower scan rates, a sigmoidal profile occurred since diffusion is competitive with the timescale of the experiment. Using chronoamperometry, diffusion coefficients measured during the in situ experiments are consistent with the reported values as well as the CV curves. Batteries, particularly lithium-ion batteries, power not only our cell phones and other consumer electronic devices, but more complex infrastructure as well, resulting in a $30 billion industry. However, when lithium batteries experience failure, it's not only costly, but a significant safety hazard. Research into developing safer, greener, and more efficient lithium-based battery materials is a top priority among research labs throughout the world. One of the key factors that affects a lithium-ion battery's performance is the formation of its solid electrolyte interface, or SEI layer, which forms along the interface of the electrolyte and the electrode. If the SEI layer is unstable, it can develop cracks and healing features as it expands and contracts over multiple potential cycles. These defects can result in the buildup of lithium dendrimers on the surface of the electrode over time, reducing the battery's efficiency and potentially causing short circuits to occur. Protochips Poseidon system offers unique working electrode materials, one of which, glassy carbon, is transparent to the electron beam, enabling you to deposit your sample directly on it without losing resolution or contrast due to the electrode material. In this example, researchers at Oak Ridge National Lab studied the growth of the SEI layer over a series of potential cycles. The image series shows the growth of the SEI layer that forms between the electrode on the left side of each image and the electrolyte on the right side of the image. The SEI layer is the the light colored line in the middle of each image, and its density and area increases with each subsequent potential cycle. In this example, researchers from the Nigel Browning and Leila Mehdi group studied the charging and discharging process using lithium hexafluorophosphate. In this experiment, they are using a platinum electrode whose surface is clearly visible. During the first charging cycle, as the potential is swept in the negative direction during the charging process, lithium electrodeposition occurs, resulting in a buildup of lithium dendrimers on the surface of the electrode. These dendrimers do not fully redissolve upon discharge as the potential is swept in the positive direction back into the electrolyte. Cycle 2 shows the second charge-discharge cycle for the same cell at a lower magnification. During the second charging cycle, even greater amounts of lithium become trapped on the surface of the electrode due to the buildup of dendrites formed during the previous charge cycle. This type of behavior is indicative of the structural changes that occur during capacity fading, since less lithium is redissolved into the electrolyte as the battery discharges, a shorter battery life results. Taking a step further, in situ electrochemistry can be used to study the impact of small chemical changes on a battery's performance. And in this example, increasing the residual water content from 10 parts per million to 50 parts per million resulted in an increasing concentration of lithium fluoride that forms during the electrochemical reaction. And in this example, that caused the formation of dendrimers with larger lithium grain sizes, but more efficient redissolution back into the electrolyte during the discharge process, and a consequently better battery life. Fuel cells are another application ideally suited for characterization using operando TEM techniques. A $30 billion industry, fuel cells provide attractive environmental and transportation industry benefits. Development of catalyst materials that are durable and resistant to degradation is a key factor to developing robust commercial systems. Electron microscopy is particularly well suited to the study of nanoscale behavior of catalyst materials during operating conditions. The development of new, more efficient catalyst materials is essential for wide adoption of fuel cell technology. Octahedral nickel-platinum catalysts supported on carbon electrodes exhibit high catalytic activity but degrade very quickly, limiting their commercial viability. In this example, researchers studied the degradation of these octahedral catalyst particles under operating conditions to better understand the microstructural changes that control their degradation. Using the Protochips Poseidon Select, they applied both sequential potential cycles and periods of constant applied potential to replicate startup and shutdown conditions. Here we see a movie obtained with in situ TEM time correlated with the applied electrochemical potential. Initially held at 0 volts, the sample is then cycled 10 times. We can see movement of the nanoparticles in the TEM image, but it is rather minimal at this point. The potential is then held again and followed by another 10 cycles. These higher voltage cycles show more movement of the particles. However, when we reach the final high voltage hold, we can see that significant mobility along the carbon support is occurring. During those potential cycles between 0 and 1.2 volts, both particle coalescence and particle motion was observed in the TEM images. In these examples, the red arrows are indicating individual snapshots taken during that portion of the potential sequence. During the CV cycling, we see some coalescence of the nanoparticles indicated by pink circles, as well as some movement of nanoparticles on the carbon support. However, when we move into the anodic hold, we see a complete rearrangement of the particles and aggregation and agglomeration. The results of this study found that the higher voltages used during the startup and shutdown contributed more strongly to the degradation of the catalyst. Thus, developing nanocatalysts that are stable under these operating conditions is key to improving fuel cell performance. In this next example, researchers focused on a commercial fuel cell catalyst, Tanaka TEC10V50E, a 3 nanometer platinum nanoparticle used in automotive applications. Catalyst degradation is one of the primary limiting factors in the adoption of polymer electrolyte membrane fuel cells. By studying the cathode reaction in situ using Poseidon Select, scientists were able to monitor the evolution of the catalyst's electrochemical active surface area to determine which structural degradation mechanisms were most impactful. Cyclic voltammetry experiments were performed in situ up to 500 cycles to replicate normal stress testing protocols. The platinum oxide reduction peak underwent a cathodic shift after the first 100 cycles, followed by an anodic shift. This indicated that the nanocatalyst underwent a reduction in size, followed by subsequent growth. Using energy filtering techniques, the researchers were able to push the TEM resolution in liquid below 1 nanometer, enabling them to follow the different types of degradation processes hinted at in the electrochemical data. These include detachment, coalescence, dissolution, growth, and Ostwald ripening. Corresponding with the sequential cathodic and anodic shifts observed in the platinum reduction peak, particle sizes measured from the TEM images followed the same pattern. In this case, we see the particles beginning to dissolve and become smaller, and then starting to grow again, following typical Ostwald ripening mechanisms. In situ TEM enabled the researchers to understand on a mechanistic level the structural changes contributing to fuel cell aging and degradation that they were able to also see in the electrochemistry ensemble measurements. Corrosion and corrosion management is a $2.6 billion industry. Corrosion affects our daily lives, from maintaining infrastructure such as bridges and pipelines to our navies and shipping industries. In situ liquid TEM enables us to look at this type of bulk scale processes at the nanoscale level to further our understanding of early stage corrosion initiation and development of corrosion resistant alloys and testing protocols. When studying bulk materials such as metals using transmission electron microscopy, it is necessary to prepare a thin sample of the region of interest. This is traditionally achieved by preparing electropolished thin film foils less than 100 nanometers thick. When performing in situ closed cell studies, the spatial dimensions of these thin films must be further reduced. This is done using a tool called a focused ion beam, or FIB, which utilizes a stream of ions that acts essentially as a cutting torch. Thus, a small region of interest can be cut out of the foil and mounted across the membrane of the E-chip for in situ liquid and electrochemical studies. Because Poseidon Select is fully compatible with energy dispersive X-ray detectors, elemental analysis can be performed in liquid. In this example, energy dispersive X-ray spectroscopy was used to follow the dissolution of a manganese sulfide inclusion in stainless steel. The inclusion is shown in the top row pre-experiment. You can clearly see the manganese indicated in pink and the sulfur indicated in yellow of the inclusion. The bottom row shows the same region after a 24-hour in situ experiment with exposure to water, and the inclusion is fully dissolved and no manganese sulfide remains. An FIB section of type 304 austenitic stainless steel alloy is shown attached to the working electrode of the E-chip to enable measurements of potentiodynamic polarization curves in sulfuric acid for comparison to bulk data. The black curve was measured in situ using Poseidon, and the red curve was measured using traditional bulk methods. The peak for the corrosion potential correlates very well for both bulk and in situ data, with differences in current density attributed to the influence of charge buildup due to the electron beam. One of the things that we've learned from working with our customers for over 10 years is that in situ electrochemistry experiments can seem intimidating and require both expertise in electrochemistry and the knowledge of an experienced TEM operator. This year, we introduced Axon, a software that redefines the in situ experience and makes in situ experiments possible for even a novice TEM operator. Axon integrates the key equipment necessary for successful experiments and enables them to work seamlessly together using machine vision algorithms that intelligently identify, follow, and correlate the features of the sample you've specified during the course of the experiment, making in situ experiments accessible like never before. Axon can be used with more than just protochip systems and can enhance any dynamic or in situ TEM session. In this example, a sample of stainless steel alloy 709 is heated from 600 to 625 degrees Celsius using a Gatan 652 bulk heating holder. The two experiments, one with Axon off and one with Axon on, are played simultaneously. With Axon off, the temperature ramp causes the sample to be highly mobile, requiring the TEM operator to make constant manual adjustments to bring the area of interest back into view. With Axon on, the sample barely appears to move at all. Axon is doing the work for you, making constant on-the-fly adjustments of the stage, beam, and camera to keep the area of interest within the field of view at all times and allowing the operator to concentrate on the sample. Thank you so much, and that concludes our presentation on electrochemical applications. At this point, I'll hand this back over to Jim McConnell, and I'll be happy to answer any of the questions that you may have. Thank you.
All right, thank you both for such great presentations. They were amazing, and I hope everybody listening enjoyed them, maybe learned something new, and hopefully has become inspired for your future research and work and what your possible capabilities are. We'll move into the question and answer section now, but before we start, I'd like to make a quick request. After the webinar, a survey will pop up, and we would really appreciate if you could take 3 seconds to answer the questions. They're all multiple choice. But within that survey, it gives you the opportunity to request more information from Protochips, from Gamry, or you can even request help in finding your closest accessible TEM facility if you're not sure. Okay, so there were a ton of questions because we've got apparently hundreds of people on here today. So I've got a handful of them, and I'm going to try and direct them, Dave and Madeline, to you guys based on who I think would be appropriate to answer. But if I don't direct it to you and you have something you'd like to add, please feel free to jump in and do so, of course. Okay, Dave, I think this first one is probably best for you. The question was basically a reiteration. What, again, is the function of the reference electrode?
Okay, so the reference electrode is there so that you can isolate the current voltage behavior of the working electrode and have a reference point, because when we measure potentials, potential scale is not an absolute scale. You have to have some kind of reference point, and so the reference electrode has a known potential that can be referenced back to the standard hydrogen potential.
Okay, great, thank you so much. For the next question, Madeline, I think this was a great one for you actually. Which electrolytes are compatible with the liquid cell TEM, or with the Poseidon Select system? Which electrolytes are compatible?
So there's, of course, there's a huge number of electrolytes that people want to use. So the main components within the Poseidon system that have to be compatible with that electrolyte are the titanium tip, the silicon nitride and silicon based E-chips, and then of course the peak tubing that delivers that electrolyte, and then the gasket. And we have gaskets of different materials, Viton and perfluoroelastomers. So we're really compatible with most things that users want to use, particularly things like dimethyl carbonates, ethylene carbonates. Those can be very tricky, but our elastomers are compatible with those for doing lithium and sodium ion battery chemistry. We have lots of users using sulfuric acid, and there's published results with perchloric acid and others. What we recommend with of course is to do some ex situ testing of this before you put it into your TEM, as well as testing these materials. We give you a full list of what is exposed to the electrolyte, and so that you can make those determinations, because there's just so many things that that people want to work with.
Great, thank you so much. Dave, I think this next one looks good for you. When do I use a galvanostat instead of a potentiostat?
When in the case of a potentiostat, when you set the potential, you're setting a thermodynamic level on the working electrode. So you're defining the chemical state of your of the electrode of interest. When you use a galvanostat, you don't actually know what necessarily what state the electrode is, what the reactions are going to be activated by passing the current through the cell. All that happens is that the cell will reactions will happen that to satisfy whatever current you request.
Okay, perfect. Let's see. Oh, Madeline, this is a good one for you. What is the best way to deposit materials or samples onto electrodes of this size?
So there's several ways that you can do that. It really depends on what the material is. So a lot, when you're studying the electrolytes, so some of that lithium battery chemistry, oftentimes they assemble everything dry and then just flow in their electrolyte and start their experiment. We recently introduced a mask system for masking samples, so that you can basically put your chip into the mask device, and it has masked out the area of the working electrode, and you can drop cast your sample, you can sputter your sample, and then deposit it directly onto the working electrode, so that it's not all over everything else. And then of course, if you're doing bulk metals, things like that, you can deposit a fib section directly onto that electrode, and we have a stub that is compatible with the e-chip that can go into your fib to make that process much easier.
Great. Okay. Dave, here's a question about electrode materials. What is a good reference electrode?
I think that's kind of difficult to answer without knowing more about what you want to use it with. Obviously, so the reference electrode has to be stable in the setup that you have. If you're using non-aqueous solutions, there are some non-aqueous reference electrodes that you can use. In general, you don't want to put an aqueous reference electrode in that kind of solution, because it might contaminate it. The typical ones are called the saturated calomel reference electrode, and the silver chloride reference electrode. Both of these have a similar potential with respect to the standard hydrogen electrode, and they're very commonly used by people doing aqueous chemistry. One of the disadvantages is that chloride is quite a contaminant in some reactions and can cause problems.
Right, okay. Perfect. And let's do one more here. Madeline, how do you know there are no spurious reactions taking place outside of the electrodes? Doesn't the electrolyte come into contact with other metals in the holder?
So that's a great question. So certainly the there's other things that could occur, particularly if you have not carefully calibrated your electron flux or your beam dose, because the electron beam itself can initiate chemical reactions. So one of the standard practices is to test these electrolytes and materials without electrochemistry first to make sure that you're not seeing any degradation or growth of other materials due to the electron beam. And so once you're satisfied that the beam is not contributing to spurious reactions, the working electrode, when you're doing your experiment in situ, it's fully visible, within the microscope. So it's fully visible on the window. There aren't parts of it that are hidden. Everything, the connections from the electrical, to the potentiostat to that window, those are embedded in an insulator, so they're not exposed to the electrolyte. Just the part of the working electrode you can see is exposed to the electrolyte, and so you can very easily, look at your electrode and look at the area off the electrode to make sure you're not seeing, that you do see a clear interface between the edge of the electrode and your electrolyte. And also, typically the magnifications that you're working at, you're not necessarily illuminating the entire part of that, imaging that entire section at once. So you can, after you run your experiment, you can move your beam and look at a part that you didn't illuminate, which was not exposed to the electron beam, as another way to control for some of those spurious reactions.
Perfect. I think there's a lot of questions here, and I think what we'll do is reach out individually to try and answer some of these, because some of them can be very individual. And so I think we'll go ahead and wrap it up after that. Thank you so much, Madeline and Dave, for joining us today, and for everybody taking the time to sit with us and listen to the presentations. I hope you learned something. And like I said, please, if you don't mind filling out the survey, we would really appreciate it, and just reach out to us if you've got any additional questions. Thank you very much, everybody.